Function continuity conditions. Where is the graph below discontinuous? Take a moment to pause this video and think about it, and when you're done, unpause it. There are actually three locations where this graph is discontinuous. It's discontinuous where we have this jump at x equals c, where we have this open hole where the curve is located and a solid point above it at point f, or at the x value of f. And then we also have a jump in the graph at x equals g. Recall the various types of discontinuity from pre-calculus. Well, there is non-removable type of discontinuity, which shows up in the form of a jump that we have here, as well as down here, and at infinite discontinuities, where you have an asymptote. There is also removable discontinuity, which shows up in the form of holes in the graph, such as this one. The graph is just discontinuous or does not exist at that one hole or point. Up until now, we have only been able to identify discontinuities in a function. We have yet to properly define what continuity is. For a function to be continuous, it must be continuous at every point in the function's entire domain. For a function to be continuous on an open interval, say from a to b, it must be continuous at every point in that interval. But how do we test every point? In order to test for continuity, we must do so at every point in the domain. Before calculus, this task would be very overwhelming. However, limits help us to test every point with ease. A function f is continuous at a point c when all three conditions below are true. First condition, the function value at c exists, or f of c exists. Number two, the limit of f of x as x approaches c exists. And the limit of f of x as x approaches c is equal to the function value at c, or f of c. It's important to note that if one of these conditions cannot be met, then we don't need to test any of the remaining ones below it. For example, if a function has a value at a point, in other words, f of c exists, but the limit of f of x as x approaches c does not exist, then clearly condition 3 will also not be true. Therefore, when explaining the part of the definition that fails, use the first or the main condition of failure as the reason. Let's try some examples. Determine if the function below is continuous. If it is not, discuss which part of the definition fails and why. To begin, we need to determine if the function value exists at point c, if the limit of f of x as x approaches c exists, and then the limit of f of x as x approaches c is then equal to the function value at c for all values of c within the function's domain. If we look closely at our function, f of x is equal to 1 over x, begin to think about what critical numbers or points we may need to think about in order to determine whether or not it is continuous. So the first step is to determine if f of c exists for all c in the domain of the function. So if we look at f of x is equal to 1 over x, we know that f of c exists for all values except c equals 0, because 1 divided by 0 does not exist. And since the function value at 0 does not exist, f of x is not continuous at x equals 0. Therefore, it fails continuity. Determine if the function below is continuous. If it is not, discuss which part of the function fails and why. We have g of x is equal to this piecewise function that is equal to x plus 1 for x values less than or equal to 0, and it is equal to e to the x for x values greater than 0. Remember, to determine if a function is continuous, we need to look at the following three things. First, we have to determine, does f of c exist for all, upside down a means for all, x values within the domain. Step number 2 is that the limit of f of x as x approaches c would exist. Again, for all x values within the domain. And the third test or property that we have to check is that the limit of f of x as x approaches c is equal to f of c. And again, for all x values within the domain of the function. Let's start testing these out. Let's start by answering our first question. Does f of c exist for all c values within the domain? Well, we know that the first piece, x plus 1 for x values less than or equal to 0, is continuous. And we also know that e to the x for x values greater than 0 is also continuous. So therefore, it should exist for all c values within the domain. Both of them are continuous on their own. The only critical point here is c equals 0. Well, when c equals 0, or the x value is 0, it would go in this first piece, and if we substitute it in there, we would get 0 plus 1, which is 1. So we have g of 0 is 1, so it does exist, and the first condition is satisfied. The second question that we need to answer is, does the limit of f of x as x approaches c exist for all c values within the domain? Well, we know for all negative x values, we would use the beginning piece, and the limit from both sides of any x value less than or equal to 0 would always exist there because x plus 1 is continuous. Similarly, for x being greater than 0, we could look at e to the first or e to the second, and it would always approach that desired value from both sides and exist. So the key piece that we need to look at is, what's the limit as x approaches 0, which is the transition point in our piecewise function. So if we look at the limit of x plus 1 as x approaches 0 from the left, and if we substitute 0 in there, we get 1. If we look at it from the right, we would substitute 0 in for x here, and we would get e to the 0, which is equal to 1. And since both of these values are the same, the limit of g of x as x approaches 0 is equal to 1. And the third thing that we have to check, or question that we have to answer, is, does the limit of f of x as x approaches c equal the function value at c? Does this exist for all c values within the domain? Well, we know for any x values that are less than 0, it would definitely work, and we could use direct substitution and get f of c being equal to the limit of f of x as x approaches c. The same would be true for x values greater than 0. We could use direct substitution, and we can evaluate the function. They would always end up being the same thing. So we have to determine, does the function value at 0, this key critical point, also equal the limit of f of x as x approaches 0? Well, we know that g of 0 is 1 from step 1, and we know that the limit of g of x as x approaches 0 is equal to 1 from step 2. And because these limits, or the limit of g of x as x approaches 0 is equal to g of 0, the function is considered to be continuous on its entire domain. Again, because all three conditions were met. Determine if the function below is continuous. If it is not, discuss which part of the continuity definition fails and why. So we have h of x is equal to sine of x. And in order to determine if it's continuous, we need to look at three things. And all three of these things would hold true for all, an upside down A in math means for all, values of c in the domain. First, we would have that f of c exists. Second condition is the limit of f of x as x approaches c also exists. And the third condition is that the limit of f of x as x approaches c is equal to f of c. Let's go through these steps to see if all of them hold true for sine of x. So the first question that we have to answer is, does the function value of c exist for all c values within the domain? So for sine of x or sine of c, does it exist for all c values in the domain? It does. Sine of x is a continuous function. It passes through the origin and continues to oscillate up and down between +1 and -1. So we know that the domain of h of x is all real numbers. Now the second question that we have to answer is, does the limit of f of x as x approaches c exist for all c values in the domain? Well, again, because we have sine of x, which is just a continuous oscillation wave, the answer here is yes, it does exist for all c values in the domain. And then, does the limit of f of x as x approaches c equal f of c? Does that exist for all c values within the domain? Well, we do know for all values of c, where c is a real number, the limit of sine of x as x approaches c will equal sine of that c value. So we can conclude that h of x is continuous on its entire domain.